Hello everyone. The topic of this presentation is what drives Southern Hemisphere subtropical anticyclones change under global warming conditions. This project was part of my PhD thesis that was supervised by Dr. Natalie Burles. As we know, solar energy distribution on Earth is not even. The equator absorbs more energy than the polar regions, and there is a polar transfer of energy from equator to pole. As a result of greater heating on the equator, warm air rises and moves poleward. Near subtropical regions, the warm air cools down and descends back to Earth's surface and creates a high-pressure ridge over both subtropical region of Northern Hemisphere and Southern Hemisphere. The cold air surface moves then equatorward again as a result of vorticity balance to rise again, and it creates circulation known as the Hadley circulation. This figure is from Aerointerium showing that annual mean sea level pressure and 925 hectopascal wind circulation. It shows there is anticyclonic systems or subtropical regions associated with Hadley circulation descending branch, and the 925 hectopascal wind shows clockwise circulation in Northern Hemisphere and anti-clockwise circulation in Southern Hemisphere. And these are known as the subtropical anticyclones. Now, although the Hadley circulation drives the zonal component of the anticyclones, numerous papers show that the local diabatic heating associated with local monsoonal heating drives the subtropical anticyclones during summer. Subtropical anticyclones are a crucial component of the large-scale atmospheric circulation. They help to transport moisture from tropics to pole. They also shape mid-latitude and tropical cyclone track. They impact radiation budget by influencing marine boundary layer clouds, acts as a forcing on local sea surface temperature and precipitation, and vice versa, and contributes to local hydrological cycle and extreme drought events. Therefore, correctly simulating subtropical anticyclones and to understand how subtropical anticyclones will change in future is very important if we want to correctly simulate the weather and climate, especially in the subtropical region and mid-latitude region. Focusing on the Southern Hemisphere, using sea level pressure and 925 hectopascal wind circulation, we have future projections minus historical projection of subtropical anticyclones from CMF5 multimodal mean on top panels and CMF6 multimodal mean on bottom panels. In both cases, it shows that anticyclones are getting more intensified in both summer and winter season, especially in the center and polar flank of subtropical anticyclones, and they also extend in the area towards pole. Now our research question is, what drives Southern Hemisphere subtropical anticyclones change in future climate? Here we have a vertically integrated diabatic heating change in atmospheric column of troposphere. The diabatic heating strongly intensifies in the tropical ocean during both seasons, especially over the ITCZ and SPCZ region. The local diabatic heating over the subtropical region of Southern Hemisphere ocean also decreases in future climate. In our previous study, we found that the local diabatic heating decrease in future over the subtropical ocean of Southern Hemisphere drives the Southern Hemisphere subtropical anticyclones, along with local baroclinicity change driven by the static stability change. However, how the tropical diabatic heating remotely influences the Southern Hemisphere subtropical anticyclones remained largely uninvestigated in previous studies. Now, to separate the influence of different forcings that influences the Southern Hemisphere subtropical anticyclones in future climate, we decompose the warming in future into two components. First, the CO2 increase in future atmosphere that directly changes the radiative forcing and changes the climate. Whereas the second part is indirect sea surface temperature warming from the CO2 forcing that in turn slowly increase the atmospheric temperature. To understand this more, we run 5 sets of CSM to CAMP6 numerical experiments with different sets of forcings. For example, the first one is forced with historical sea surface temperature and CO2 forcing from CMF branch. Then we run historical sea surface temperature and CO2, but we artificially add diabatic heating changes in the tropical ocean from future climate to the model to understand how the tropical diabatic heating alone influences the subtropical anticyclones in future climate. The third set of experiment forced with future SST, but historical carbon dioxide to find influence of the sea surface temperature alone. then another set of featured CO2 but prescribed historical sea surface temperature to find the direct CO2 influence in the atmosphere, but not SST influence in the future climate. Finally, we run the model with both future SST and CO2 to see as a combined effect how they influence the subtropical anticyclones in future. Here left panel shows DJF mean climatology of vertically integrated diabatic heating, showing intense heating over southern hemisphere land during summer and heating over tropical ocean over the ITCZ and SPCC region. Right figure shows the diabatic heating change from CMIM6 models coupled simulation. Now we want to see which of our first run experiments shows similar changes in diabatic heating to the top right panel of CMIM6 diabatic heating change. Here we have left middle panel as diabatic heating first, middle right as the SST first, bottom left CO2 first, and bottom right SST and CO2 first combined. The diabatic heating first run shows how much heating was added artificially. Clearly, the tropical diabatic heating increase in future climate is a result of tropical SST increase in the future climate through the Clausius-Clapeyron relation process that we know, whereas the direct CO2 increase acts as a secondary forcing to change the net diabatic heating in the atmosphere. Now here we have sea level pressure change in DJF mean similar to our last slide. Just to iterate again, we want to see which of the bottom first experiments comes closer to anticyclones change that we see in the top right panel from CMIM6 projected change. The middle left panel, diabatic heating first run, doesn't show any similar changes in sea level pressure in the southern hemisphere subtropical ocean compared to top right panel during DJF mean. This means the tropical SST change that drives the tropical diabatic heating doesn't necessarily influence the DJF mean changes of subtropical anticyclones in the southern hemisphere. Whereas the SST and CO2 first run shows similar sea level pressure changes associated with subtropical anticyclones in the southern hemisphere during DJF mean, especially the SST first runs. This is due to the local diabatic heating changes and directly local static stability changes in the mid-latitude southern hemisphere, mostly forced by the local SST change. Here we have southern hemisphere June, July, August mean diabatic heating changes from our experiments, same figures as before for DJF. Now, similar to DJF mean, we can see that the tropical diabatic heating change is directly forced by the SST warming in the tropics in June, July, August too, whereas the CO2 forced radiative forcing has a secondary component to the atmospheric heating change. Now, if we look at the sea level pressure change in southern hemisphere winter in June, July, August, the tropical diabatic heating forced by the tropical sea surface temperature increase plays a more significant role compared to DJF. Both middle panels looks very similar due to large influence of tropical SST driving the tropical heating that remotely influences the southern hemisphere subtropical anticyclones rather than the local sea surface temperature that we see in DJF. This is not so surprising given many literature has shown that how climatologically during southern hemisphere winter or northern hemisphere summer the interhemispheric transport of energy from northern hemisphere to southern hemisphere winter is more strong due to northern hemisphere monsoonal heating relatively being more stronger as we have more land in the northern hemisphere. The South Indian subtropical anticyclone increase in future is driven by both tropical heating and CO2 increase. The South Pacific subtropical anticyclone increase in future is mostly driven as a combined effect of SST and CO2 forcing. In summary, the indirect local sea surface temperature warming in future climate dominates the southern hemisphere subtropical anticyclones change through changing the static stability that leads to reduction of baroclinic eddy growth. Exception to mechanism is DJF South Pacific subtropical anticyclone and June, July, August South Atlantic subtropical anticyclone. The direct radiative forcing from CO2 increase plays a secondary role. A combination of direct radiative forcing due to CO2 increase and indirect sea surface temperature warming acts as a forcing to increase the DJF South Pacific subtropical anticyclone. The tropical diabatic heating change forced by the tropical sea surface temperature acts as a remote forcing to change the subtropical anticyclones in the southern hemisphere through baroclinic eddy growth and zonal wind shear during June, July, August. Due to time constraints, we didn't go deep into mechanisms, for example, stake stability, zonal wind shear, or Berkeley change with different boundary conditions. If you're interested, I recommend to look into these two of our studies. Thank you.